Hello everyone. In our today's session, we'll conduct experiment with respect to linear convolution for given sequences. So myself Sri Shana, Assistant Professor, Department of Electrical and Electronics Engineering, ATM College of Engineering, Mysore. So here we'll evaluate and check how with respect to two different sequences, when we combine, how the output is basically going to perform. So before understanding linear convolution, let us first quickly walk you across with respect to what a convolution basically means. So here you can basically check out we have a convolution that relates to an input signal and impulse response of the system that is going to give you an output response. Let's say, for example, in very simple terminology, if I have an image out here and if I have a mapping kernel, something like, let's say for example, you want to identify X person's identity, something like, let's say in terms of police verification. So they have a list of database where they are trying to convolute and find out the eye pattern of a particular person. So if it is matching or not, they'll try to extract the features of that. So if from the input image, which is already available with them of some X person, and they have a set of identified database which is pre-documented, that is feature extraction, they'll try to match it and try to get the output of it, whether it is actually coinciding and is it the same person. So this can be used in number of applications. Here we have a different mathematical multiplication that is happening around ultimately to give you some output. So if I have to speak about the applications, there are different applications. It can be used in probability, statistics, acoustics, spectroscopy, signal processing, image processing, geophysics. It can be computer vision, differential applications, and numerous applications as such. So when we talk about linear convolution, in very simple terminology, you will be having two sequences, one input signal, which I just showed you in the form of an image, and an impulse response, that is h of n, and finally we'll be getting some output response, that is y of n. So here basically multiplication of those two sequences in time domain analysis is your linear convolution. So basically input signal, that is your input signal sample is x of n, impulse response, and finally you are getting your output. So let's say for example, if I have the number of samples here as 10 and the number of samples here as, let's say, 4, ultimately when you are going to get the output of this will be n minus 1. That is, if you are having 15 samples, 15 minus 1 is the elements or samples that you are going to get in the output. So if we talk about linear and circular convolution, here when we talk about linear, the two signal sequences, that is x of n and h of n, is given by the same system and you are finding out the output. But here it is multiplication of two discrete Fourier transforms. So when we talk about linear convolution, again multiplication of two sequences in time domain and multiplication of two sequences in frequency domain. So here is a correlative equation with respect to x of k and h of n minus k, that is going to give you your y of n. And we'll discuss about circular convolution in detail when we are discussing about this in our subsequent experiments. So the objective here is to perform linear convolution of two given sequences and to verify the linear convolution using simulation 2, that is Octave. So here you are using 5.1 as the version. So I have taken up a sample example where the input sequences x of n is 1, 2, 3, 5, 7, 8, 9 and h of n is 1, 2, 3. So if I have to solve this, first put up the samples in the form of a table like this. So 1, 2, 3 is your h of n, that is the impulse samples, and x of n is 1, 2, 3, 5, 7, 8, 9. So once you are done with this, just multiply each of the sample, 1 into 1, 1, 1 into 2, 2, 1 into 3, 3, and do this so up till 9. Similarly, 2 into 1, 2, 2 into 2, 4, 2 into 3, 6, 2 into 5, 10, up till 2 into 9, 18. Similarly, 3 into 1, 3, 3 into 2, 6, 3 into 3, 9, up to 27. So once you are done, map it diagonally and try to mark it in the form of a representative simple blocks. So here you can see there is a diagonal representation 1, 2, 3, 4, 5, 6, 7 and 8. So 8 different lines that they have indicated ultimately should give you this many samples. How? So first representation is retained 1, 2 plus 2 is 4, 4, 5, 6, 7, 8, 9, 10, 6, 12, 17. Next comes 26, next comes 37, next comes 46, next again 42, and lastly 27. So if you count the number of samples, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 minus 1 is 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 samples is what you are getting as output, which we just came across in the previous slide as n minus 1 sample elements. So here in the program, when we just talk about the flow that we are going to get, so here you can basically check out the first two is option that you all can basically type. CLC is basically you're clearing the workspace. Here helps you in clearing the matrix grid. So basically, if I am to enter the sample of first sequence that we just came across, that is 1, 2, 5, 7, 8, 9. So I have to enter that first sample's x of an input sequence. So I'm entering my first sequence, and I have taken a consideration of plotting that using my subplot command. So I'm taking a matrix grid in the form of 3, 1, 1. So 3, 1, 1 means if I have, let's say, 3 rows, and in that first particular representation, that is the first row, where you'll be having 3 rows, 1 column, and the first image in that column. So stem is something continuous to discrete representation that we are going to plot up with respect to our first sequence. So whatever sample sequence that we are getting, that will be represented in discrete form. And finally, to know our representation, we have given the plot representation title as plot of first sequence. Similarly, the impulse response is given by H. So again, second sample 1, 2, 3, we are going to give the values over here, and that in the form of representation of discrete when I want 3, 1, 2, that is in the second particular representation, because already we have taken 3, 1, 1, so it will be appearing in the second particular row. Next, plot of second is the title that we are going to indicate with respect to our second sample. So once we are done, we take the convolution. This is the main command that is going to give our actual performance. So convolution 2 is the command that will help us in convoluting the two samples x and h, and that will be given out in y. So once this is done, we'll display our output y, and that is representative indication output of linear convolution as the informative in the image. So x label and y label, that is with respect to time axis and with respect to amplitude. So finally, the third image will be appearing in the bottom of the row. So third row, first column, in the third division of my first column, I'll be getting the image. So finally, I'll plot the discrete representation of the output that I've got y, and finally the title with respect to this. So to show this, you'll be entering the first sequence, what we had just come across, second sequence, and finally you'll be getting the convoluted linear sample of this. And here is the response that I just spoke about. So first row, second row, third row, 3, 1 was the first image, 3, 1, 2 is the second image, 3, 1, 3 is the third image. And here you can basically see the output that we basically got with respect to our result that is available over here. So the same representation is indicated over here, that is 1, 4, all the values that you just saw in our previous slide. Now, when I have to show this in real representation, so let me just go and copy this particular program. So I'll copy this. In your case, you have to type. So I'll just open up Octave window. Software, and let's see. So let the window open. Meanwhile, we'll just check. Okay. So let me just minimize. I think I've clicked out multiple times. So let me close out the window. So I'll come to the editor window and I'll just paste it. So now I'll save the file. Save file. So I'll save file as, let's say, experiment 3. I'll save it. Run it, and let me enter my first sample signal. So let me keep it side by side. So 1, 2, 3, 5, 7, 8, 9. So I'll 1, 2, 3, 5, 7, 8, 9. You can also put a comma and enter the sample. So here you can check out the first plot response. If you want directly, you can have it at the last as well, since we have used the stem command in the initial. As soon as you type and execute, immediately you'll be getting the first response. 1, 2, 3. I think we have taken up 5, 7, 8, 9. Second one is 1, 2, 3. So let me enter the second sample. 1, 2, 3. We'll be getting a second sample as well. And finally, the output of this. So if I just show side by side, so here you can basically check out. That is, we have got 1, 4, 10, I think 17. We have got 26, 40, 37, 46, 42, and lastly about 27. So this is our plot response with respect to the samples. So 1, 4, 10, 17. Here you have to see in the vertical y axis and check out the output, that is with respect to the amplitude. So this is all with respect to the linear convolution of sample. Thank you.